Hello students, this is Professor Smolny. Based on the email that I sent you guys out today, I hope you all know that I wasn't feeling too well. So I'm just going to go ahead and record Chapter 5 tonight, and we're going to go over the midterm next week in person at a regular meeting spot in the science building. Also, I hope to have some materials prepared for the projects, kind of a framework so that you guys can get a better understanding of what the direction is that I want. And hopefully this will help guide your development of the project. So we are going over Chapter 5, Expert Systems. Chapter 5 homework will be assigned today, so the questions at the end of the chapter, and it will be collected, or you guys should email it to me by the start of next week's class on the 25th. So let's just jump into the lecture. So, expert systems, capturing high-level knowledge and improving behavioral control. What are the key chapter questions for Chapter 5? What are the three components of an expert system? Which part is created in advance, and which is modified during the use of the expert system? What are the two styles of inference engines? Which is more suitable for games and why? Which style of inference engine is more suitable when we only know some of the facts? What is the name of an expert system that uses this method? When an expert system is embedded in a game, what is the source of facts? Do we have partial or complete knowledge? What are inconsistent facts? Describe two mechanisms to handle them. So, what is an expert system? Basically, these are constructs of capturing knowledge from an expert. So, in the real world, there are people who have vast knowledge about certain topics. We call them experts. Unfortunately, we don't always have them, at our fingertips. In order to take that knowledge and come up with ways to basically mass produce it so that it can be used over a variety of different applications, we have an expert system. So basically, you pick the brain of the expert, and from that, you can devise roughly what we'd call a computer program that could answer questions and hypothesize about the current state of a particular system with that same accuracy of the expert. So what are the three pieces that are responsible for this? First off is the knowledge base. So this is the knowledge that an expert would have, kind of like the logical statements that they would control in their head. So this applies beyond games. This could apply to medicine, as the book goes into a couple examples of how this works. But an expert knows that if a certain condition is met, then a certain action should be taken. So this is, if the patient looks sick, then give them a certain medicine so that they're healed. Same logic can be used in games. If the player needs to be challenged, attack them with X number of units. So that's what the knowledge base is. It's a set of rules that basically define how we're going to engage the user of the system. The next piece is the working memory. So these are all the facts that you currently know to be true. So these are, in the case of medicine, it would be, the patient has a fever, they threw up, their temperature is 2 degrees above normal, whatever else, their glands are swollen. In this example, it's the example of operating a car. So it's, what is the current state of the light that's in front of you? It could be red, it could be green, it could be yellow. Only one of them can possibly be true. In the game, it might be something like, the player has X number of units, or the current difficulty setting is easy, so on and so forth. So the working memory is all the current facts that are true. And so then the last piece is the inference engine. So you take your rules, so this is the knowledge that you've basically picked the brain of the expert, plus your working memory, so all the facts that you know to be true, and use what's called an inference engine to basically put the two together. So An inference engine is not unique to any one application. So this could be, same inference engine could be used to figure out whether somebody is sick or not and what the best treatment of that patient is. It could also be used for games, many other different uses. So you take your working memory, let's say in this case the fact that the red light is on, and suppose there is a rule that if the red light is on, then you should stop. So putting those two together, you find out that, okay, the left-hand side of this equation, the if part of it, is being fulfilled by the current working memory, the current facts of the state. Therefore, we should definitely take the action on the right-hand side. So that's what that last part is, the new working memory. We know the red light is on. We can infer from our rule set that we should stop. And this could go on for several steps after this. If the new working memory now had another fact that applied to another rule in the rule set, we could go on down the line, so on and so forth, until we get to our final action. So how exactly do we capture high-level knowledge? So how do we build our our knowledge base? There are two main ways. One is through analysis. So you could try and mathematically come up with, a understanding of what the parameters should be. So in the case of the car, you want to stop, you got to figure out, what's the average stopping time, how quickly could the person apply the brake, what's the average delay time, is the road wet? All of that will basically determine how and when our rules should tell us to stop. So that, if we've only got 200 feet to stop before the red light, we can actually stop, or if we should just run the yellow because we won't be able to stop anyway. The other way, rather than just doing it mathematically, is to do empirical stuff. And what that basically means is, in the case of driving, you could go out into the real world and actually just record, how much time it actually takes for somebody to stop the car, or what the average stopping distance of a whole series, like a whole range of cars could be. You could take the average, and that could work as our new basis for our knowledge. So one is mathematically kind of deriving from the environment, the other one is sampling from the environment. So one of the challenges in expert systems is that, depending on what your data is, you can have conflicting information. It's not necessary that your knowledge base be very detailed. It could be very high level. And so when things are abstracted away, it's very easy for it not to be, for inconsistencies or potential conflicts to arise. When things are very specific, and what they're saying here, deep knowledge is self-consistent. When things are very specific, it's very easy to make sure that there are no conflicts. You know exactly where the car is, you know exactly what state it is in. Great. When you're using high-level terms like the car is moving, the car is, far away from a red light versus right upon a red light, it's not really clear-cut where the current state of the item is, or in this case the clear state of not really clear, the state of the system. And like I said, this can cause problems because, am I far away from the red light or am I near to the red light? It's a gray area. And so this can result in inconsistent results. So I may have a system where I am told to both stop and go at the same time. Now obviously you can't stop and go at the same time. You can do one or the other.